Okay, let's look at AP topic 7-5. This is a BC topic, and this is called Euler's method. It looks like Euler, but you do say the word as Euler. It's named after mathematician Euler. Okay, so basically, as we go farther into Unit 7 of AP, we know how to get particular solutions for differential equations. However, sometimes we're presented with differential equations that we either cannot or cannot easily figure out the particular solution for. So Euler's method is a way to approximate a solution if you don't know the particular solution or if you're just asked to do it, which is what would likely happen on an AP test. So here we go. You're going to be given a differential equation. We're just going to do one example. They're kind of long. Let's imagine that you're given a differential equation, dy over dx equals 3x minus y. Now, it could be listed as y prime equals 3x minus y. And, just be aware that there are different ways to show that it's a differential equation with x, y, and a derivative in it. Okay, so we have our differential equation. Now, whenever we approximate with Euler's method, we have to have a starting point. We have to have a point that we know. So maybe we're told that y of 0 gives us 1. So that's a starting point of x equals 0 and y equals 1. Then another thing you're going to be given is you're going to be given steps. See, Euler's method is a way of approximating if you know the slope, like we can calculate the slope of 0, 1 in this differential equation by plugging it in. So we can know the exact slope at the point 0, 1. But right next to x equals 0, like maybe x equals 0.1, we don't know that slope. But Euler's method gives us a way to have a reasonable approximation of what that slope might be like right next to x equals 0. And so Euler's method is a way to approximate maybe a little farther away from x what a slope might be. And what you'll be given is you're going to be given a step. And I'm going to let h be the step. And let's say in this case we're told that we want our step to be 0.2. So that's how far we want to keep approximating away from x, the new slope. Now, you might be given an actual step size on an AP exam, or you might be told to use the domain 0 to 1 with 4 equal steps. So then you would, going from 0, x equals 0 to x equals 1, divide that by 4, and your step size would be 0.25. So this is all the information you're going to be given. And you're going to be asked a few different questions. You might be asked to approximate a value for y after so many steps. Or you might be asked to approximate a value for y given a new x. Like maybe we want to look at x equals 1. So with a step size of 0.2, that'd be 5 steps away. We might just be it might say give a value of y, approximate a value of y after 3 steps. So there are a couple of ways that the question can be asked. Then there are other things that you can do with it. It might ask you for the equation of the tangent line after 5 steps. So then you can work out everything we're going to work out and then plug it in a point slope form. You might solve for like a k, missing k value from the original point, like maybe we don't know the y part, or we don't know the x part. There are different things you can do. But let's just go through a basic example of how this works. But the key thing is that you're given the information above. You're given a differential equation right here. You're given an original point, and then you're given a step size, or you figure out the step size based on other information. Okay, so what you want to do is you want to make a table. And our table is going to have an x column, a y column, and a dy dx column. Now, how many rows need to be on our table? Well, it just depends. In this particular problem, let's imagine that it asks us to find, maybe the instructions would say approximate the y for x equals 1. And we're already given a step size. So we're going to have to start at x equals 0, which is the point we're given, then approximate it at 0.2, then 0.4, then 0.6, then 0.8. Then finally we'll get to x equals 1, and we'll be getting our approximate answer from there. So what we're going to do is we're going to follow some steps, and these steps are critical. It's going to take you a little bit of practice to get used to them, but they do take a while. So we plug in our original x and our original y into our first row. Now we're going to take that x and y and plug it into our differential equation to get out the dy dx at that point. And so this really shouldn't be that big of a deal. We're just going to say, okay, so 3 times 0 minus 1 is -1, and that gives us a dy dx of -1. First row is not that big of a deal. Okay, so now let's go to the second row. So here we go. The second row is going to be taking whatever our original x was and adding to it our new step. So now instead of looking at 0, we're going to look at 0.2 higher than 0. So we're going to look at 0.2 for our new x. Now, here's kind of the other new thing that you have to get for Euler's method. It's all about finding the new approximated y based on the information we have in the table already. And I'm going to write a little formula over here, and it goes something like this. The new y, we'll say y sub n, is equal to the last y, so whatever the previous y was in the last row, plus your step size times the last derivative. Okay, so let's figure out our new y here. So our new y is going to be our last y1, okay, coming from right here. Then we're going to go plus our step size, and the step size was given to us in the problem, 0.2, times our last derivative, -1. Okay, so there you go. That's really important. You're going to have all of that into a calculator, and you're going to work it all out. These are 100% calculator problems. And you're going to get a new y of 0.8. Now what happens with these is a lot of times you get decimal answers, and then the decimals get crazier and crazier the farther you go. Okay, now we need to calculate our new derivative with our x and our y. So we plug those into dy excuse me, over dx, and we get -0.2. Okay, from here it is just a matter of repeating these steps until you get up to where you were asked to make it to. We were asked to approximate for x equals 1. So, I can just go ahead and show you that, we're going to have to figure out at 0.4, at 0.6, at 0.8, and one more. We're going to have to go all the way to x equals 1. And we're looking for the answer, the y, that's going to come out right there after we have gone through Euler's method over and over and over again. And I'm not going to take the time to walk through every step now for the next 4 rows, but let me just talk it through, and then I'll give you the numbers and you can try it on your own. So we're always finding the new y, and that's over here. It's always the last y plus the step size times the last derivative. So for instance, to get this new y, we're going to take the last y plus the step size times the last derivative. Okay? And so all of that is going to work, and we'll get 0.76, and then we'll plug our x and our y for this row into the differential equation, and we'll get out a dy dx for this row of 0.44. And then we just keep going. 0.848 would be the next one, 0.0952, 1.0384 would be the next y, 1.3616. And then finally, we get to where we were asked. We were asked to approximate y for x equals 1. We had our step size of 0.2, so we had to keep working every 0.2 up till we got to 1. And so now we're going to use this equation to figure it out. So our last y plus our step size times the last derivative. And that gives us, excuse me, a final answer of 1.31072. And there you go. That is the approximation for y at x equals 1. Now, it's just an approximate particular solution. It's not the exact solution. Now, as you move farther into calculus, and you might remember from calculus AB, you can find particular solutions of differential equations by separating the variables and then solving out from there. However, maybe this is an example where we can't easily do that, and so Euler's method can give us an approximated solution. But if you're given a problem that you can find the original particular solution for, then what you might be asked to do in an AP question or maybe on a free response would be then to take your approximated answer and then take the actual real answer and subtract them to figure out what the error is, or how far apart they are. But hey, there you go. That is Euler's method, AP Calculus BC, Lesson 7-5.